Now to an incredible find overseas, an elaborate series of stone monuments believed to have been hidden for thousands of years, not far from the famous site of Stonehenge.
Now, a new analysis shows that the 6-ton iconic altar stone at the heart of Stonehenge originated from northeastern Scotland.
There is a field in southern England where something impossible was built. It sits on the chalk plains of Wiltshire, roughly 90 miles southwest of London, rising out of flat farmland with a kind of quiet authority that has unsettled every person who has ever stood before it. Not because it is beautiful, though it is, but because it should not exist. Not like this. Not here. Not built the way it was built, by the people who supposedly built it. Stonehenge has been studied for centuries. Measured, surveyed, debated, carbon dated, and theorized into the ground. Medieval chroniclers handed it to giants and wizards. Victorian romantics gave it to the Druids. The 20th century handed it to Neolithic farmers with ropes and logs and enough patience to move mountains across counties. Every generation has had its preferred explanation. Every explanation has quietly buckled under some detail that never quite fit. And now, in the most comprehensive reanalysis the site has ever received, that entire stack of explanations is being put under pressure in a new way, not by a rival theory, not by a fresh dig, but by artificial intelligence. Researchers have fed the most complete dataset ever assembled on Stonehenge, spanning 3 centuries of surveys, measurements, geological scans, and astronomical calculations, into advanced computational systems, asking them to do what no individual human career could: look at everything at once, and report only what the numbers themselves demand. What has come back is not a simple story. It is, if anything, the opposite. The more precisely we can now read this site, the harder it becomes to explain. Before getting into what the AI found, it is worth sitting with what Stonehenge actually is, physically, materially, in a way that the photographs tend to flatten out. The outer ring is composed of enormous sandstone blocks called sarsens. Each one stands more than 20 feet tall. Each weighs in the region of 25 tons. They were quarried from Marlborough Downs, roughly 25 miles to the north, and dragged across open country, then raised upright and capped with horizontal stone lintels. Those lintels were not just dropped on top. They were locked into place using mortise and tenon joinery, the same interlocking joint technique a carpenter uses to connect furniture, carved here into solid stone by people who, according to the archaeological record, had no metal tools to do it with. Inside that outer ring sits a horseshoe arrangement of even larger structures called trilithons, pairs of uprights topped by a single lintel, the tallest of which stand over 24 feet. And then inside those, the blue stones. Smaller, typically weighing between 2 and 4 tons. And here is where the story becomes genuinely strange. They came from the Prehistoric hills of southwest Wales, approximately 150 miles away. Across rivers, hills, and open sea channels, with no wheels capable of bearing their weight, no metal tools, and no written plan that has ever been found. The textbook answer has always been rope, logs, human labor, and time. Generations of effort, slowly accumulated. It is a dignified answer. It is also one that has never been fully demonstrated. Modern engineers, equipped with steel and hydraulics and every advantage of the 21st century, have sweated over attempts to replicate even a single stage of the process. The results have been instructive in showing how difficult it is, rather than proving how easily it could have been done. But the bluestones made the journey. That much is certain. The stones are there. They arrived. The question that researchers are now asking, aided by computational tools that can process the full weight of accumulated data simultaneously, is not simply how they were moved, but why those specific stones from that specific location were considered worth moving at all. The answer, it turns out, may have nothing to do with geography or faith, and everything to do with sound. In 2013, a research team from the Royal College of Art led by Paul Devereux and John Wozencroft traveled to the Prehistoric hills and did something straightforward. They struck the stones. After testing over 1,000 rocks along the Carn Menin Ridge, where many of Stonehenge bluestones originated, they found that between 5 and 10% of the stones ring when hit, producing clear, metallic, bell-like tones. In localized hotspots, the figure climbed to 20% or higher. Rocks with this property are known as lithophones, and they are not common. The local sarsen stones of Salisbury Plain, plentiful and far closer to the building site, do not ring the same way. The Prehistoric village of Mainclachog, the name itself translates from Welsh as bell stones or ringing stones, used bluestones as church bells until the 18th century. This was not accidental. The people living in that landscape knew what those stones did. And whoever chose them for Stonehenge knew it too. Different bluestones, when struck, produce tones at different pitches, varying according to their size, shape, and mineral content. Researchers have found that the specific selection of stones used at Stonehenge encompasses a range of frequencies. Some acoustic archaeologists have suggested the selection is not random, that the stones were chosen to produce a harmonic range when played as an ensemble, a prehistoric lithophone instrument assembled across a 150-mile journey and installed at the center of one of the largest ritual structures in the ancient world. This claim is difficult to fully verify with what remains, since many stones have been broken, displaced, or are missing entirely. But the starting point is solid. These stones were chosen, at great cost and effort, from a place known for their acoustic properties, when functionally equivalent building material lay far closer to hand. Ruins of Stonehenge are not Stonehenge as it was. Centuries of collapse, looting, vandalism, and weather have left the monument a partial skeleton. Studying the acoustics of what is standing today tells you relatively little about how the completed structure behaved. To solve this problem, acoustical engineer Professor Trevor Cox of the University of Salford built what he called Minihenge, a precisely constructed 1/12 scale model, incorporating data from laser scans of the actual site and archaeological evidence about the original configuration. The model was built to replicate the acoustic properties of the real stones rather than their visual appearance, using materials treated to match the sound absorption and reflection characteristics of the original sarsen and bluestones. Speakers and microphones were placed inside and around it, and a series of experiments were run in a specialist acoustic chamber at the university's Acoustics Research Center. The results, published in the Journal of Archaeological Science, were striking. The completed Stonehenge would have functioned as a resonant acoustic space, amplifying speech and music for people standing inside the circle by approximately 4 decibels, while significantly containing sound within the structure rather than projecting it outward. People outside would have heard much less. People inside would have been enveloped. The reverberation time, the measure of how long a sound sustains before fading, was estimated at around 0.8 seconds, giving the space what Cox described as a cavernous quality that would have made a small group of chanters or drummers sound far larger and more powerful than they were. Research into the infrasound characteristics of the space, frequencies below the threshold of conscious hearing, has added another layer. Some acoustic archaeologists have noted that Neolithic stone enclosures, including chambers in England and Ireland, resonate at frequencies in the range of 95 to 110 Hz. This range corresponds closely to the resonant frequency of the human skull's cranial cavity, and neuroscience research has established that sustained exposure to sound in this range can produce measurable shifts in brain activity. Specifically, a shift toward the prefrontal cortex associated with altered states, heightened emotional sensitivity, and meditative or trance-like experience. Whether Stonehenge was deliberately engineered to produce these effects, or whether the acoustic properties were a byproduct of decisions made for other reasons, is something the data cannot definitively settle. What it can say is that the finished monument, in its original complete form, was not acoustically neutral. It was an extraordinary sonic environment, and its builders chose materials from 150 miles away that was specifically known to ring. In August 2024, a study published in the journal Nature revealed something that overturned more than a century of assumptions about the most central stone at the site. The altar stone, a 6-ton slab of sandstone lying flat at the heart of the monument, partially buried under 2 collapsed sarsens, had been believed for over 100 years to come from Wales. Repeated attempts to match its geochemical signature to Welsh rock formations had drawn a blank. The research team, led by Anthony Clark, a doctoral student in geology at Curtin University in Australia, used laser ablation techniques to fire beams into the mineral crystals of a fragment removed from the altar stone in 1844. By analyzing the ratios of uranium and lead within the crystals, they could establish the age of the minerals that had cemented together to form the sandstone, a technique from geochronology that functions as a kind of molecular clock. They then compared these results against known rock formations across Great Britain and Ireland. The match was unambiguous. The altar stone came from the Orcadian Basin in northeast Scotland, a straight-line distance of at least 700 kilometers from Stonehenge, making it the longest known stone transport in the history of Neolithic monument building anywhere in the world. We couldn't believe it, Clark told reporters after the paper's publication. His co-author, Professor Nick Pearce of Aberystwyth University, stated simply, the only area where there was a match was northeast Scotland. The implications are significant on multiple levels. A journey of 700 kilometers, through forests, across rivers, and almost certainly by sea, required logistical coordination of a scale that most models of Neolithic society struggle to accommodate. Parker Pearson, one of the leading archaeologists of the site, has noted that the findings point to connections between communities across Britain that were far more sophisticated and far-reaching than the traditional picture of isolated tribal groups. The altar stone's origin suggests Stonehenge was not a local project. It was something that drew resources, material, and presumably people from across the entirety of the British Isles. And it raises the question that always follows the logistics. Why? Why that specific stone, from that specific location, dragged or floated 700 kilometers to lie flat at the center of this particular monument? No one has yet answered that question convincingly. The science has located where it came from. The reasoning behind the choice remains, as it has always been, out of reach before the sarsen stones were raised, before the bluestones arrived. Stonehenge builders dug a ring of 56 chalk pits just inside the outer earthwork bank. They are called the Aubrey Holes, named after the 17th century antiquarian John Aubrey, who first spotted them in 1666 without fully understanding what he was looking at. For most of the century since, neither did anyone else. Some pits held cremated human remains. Some were empty. The spacing between them appeared irregular enough that for a long time, the irregularity was attributed to the imprecision of people working with antler picks in chalk. That explanation did not survive rigorous modern analysis. Astronomer Gerald Hawkins first proposed in the 1960s, using an early IBM computer to check alignments, that the 56 holes were not merely pits but a functional astronomical device. His work in Stonehenge Decoded argued that markers moved between the holes could track the moon's 18.6-year nodal cycle, the period over which the moon's rising and setting positions swing through their full range, and thereby predict lunar eclipses. Subsequent researchers, including Fred Hall, developed the model further. The number 56 itself is telling. 18.6 multiplied by 3 equals 55.8, which rounds cleanly to 56. 3 complete lunar nodal cycles, encoded in chalk. When the spacing between all 56 holes is measured precisely and plotted, the gaps trace a pattern consistent with the moon's orbital variation across the nodal cycle. The positions where the holes are closer together correspond to periods of slower apparent movement, and the wider gaps correspond to the faster periods of the cycle. This is not the kind of pattern that emerges from people digging at rough intervals. It is the kind of pattern that emerges from people who had been watching the moon's precise rising and setting positions for at least one full 18.6-year cycle before they ever broke ground, recording observations across almost 2 decades and then translating that accumulated knowledge into physical distances, accurate to the centimeter, around a circle 100 meters wide. The astronomical alignment capabilities of the full monument extend well beyond the famous summer solstice sunrise. Hawkins' original computer analysis in the 1960s identified 13 significant solar correlations and 11 significant lunar correlations with the monument's features. More recent work, using modern computational tools and far more complete datasets, has refined and expanded this picture. Researchers have confirmed alignments, tracking the lunar standstill extremes, the moments every 18.6 years when the moon reaches its maximum northern and southern rising and setting positions. Additional alignments mark cross-quarter days, the astronomical midpoints between the solstices and equinoxes, which are now understood to have been significant throughout the prehistoric calendar in Northern Europe. What AI-assisted analysis adds to this picture is not primarily new discoveries in isolation, but the capacity to look at the full dataset simultaneously. Human researchers studying one feature at a time, across careers that inevitably ended before the project was complete, could identify patterns within their area of focus. What they could not do was hold all of it at once and look for the connections between patterns, the way the lunar calculator in the ground relates to the acoustic properties of the stones above it, which relate to the astronomical alignments of the monument as a whole. Computational analysis can do that. And what it reveals is not a collection of independent clever ideas, but what appears to be a single integrated system designed from the beginning to operate on multiple levels simultaneously. The monument itself, taken in isolation, is astonishing. But recent analysis, using LiDAR aerial scanning technology that penetrates vegetation and topsoil to reveal buried features, has shown that Stonehenge was never meant to be taken in isolation. It is the most famous point in a landscape that was comprehensively shaped across thousands of years. Burial mounds, ceremonial avenues, earthwork enclosures, timber circles, and pit alignments extend for miles in every direction around the monument, connected by geometric and astronomical relationships that are only visible from above or through computational mapping. Some of these surrounding features form precise geometric relationships with Stonehenge at their center, triangular arrangements between burial mounds with the monument at the apex, earthworks running dead straight for kilometers aligned with solar and lunar events when sighted from specific positions. The accuracy required to place features this far apart and still hold the geometry tight to within a few meters represents a level of surveying skill that scholars have historically associated with classical Greece, approximately 2,000 years after Stonehenge's main construction phase. Crucially, some of the earthworks and mounds wired into this larger geometric network predate the stone circles. They were built between approximately 3,500 BCE and 3000 BCE, anywhere from 500 to 1,000 years before the Sarsen trilithines were raised. This means the landscape blueprint existed first. Stonehenge was not the beginning of the project. It was added into a geometric and astronomical framework that was already laid into the ground when the stones arrived. Somebody designed the master plan, then their descendants, across 20 to 25 generations, continued executing it with sufficient accuracy to complete it. With no writing, with knowledge passed entirely by memory and demonstration, in a form stable enough to hold tight geometry across half a millennium. That is the part that compresses under scrutiny in the most interesting way. Even the most stable oral traditions in human history, the Vedic hymns of India, the Homeric epics of Greece, show measurable drift over centuries. They change. They simplify. They lose technical precision even as they preserve poetic form. What the landscape around Stonehenge requires is something tighter than anything we have documented in the ethnographic record. The knowledge needed to place the next monument in the correct position, kilometers from the last one, aligned to a plan drawn by someone who had been dead for generations, had to be passed forward with a fidelity that oral tradition has rarely, if ever, demonstrated. Here is the finding that modern computational analysis has made sharpest, and that sits most uneasily against the usual story of human progress. Stonehenge did not improve over time. It peaked at the start, and declined from there. When the radiocarbon dates, the architectural relationships, and the geological sequences across the full build are laid out together and examined for patterns of precision, the earliest work consistently shows the highest accuracy. The first bluestone arrangements reflect the deepest understanding of the site's acoustic potential.